Okay, let's see if in 15 minutes we can do a pretty good job with the idea of inverses, inverse functions. This is section 1.5 and the last section in chapter 1, inverse functions. All right, well, we're going to start talking about how you find a function and its inverse. So we're going to start with the algebraic definition. So let's start with a function that we are, that's not difficult. Let's take f of x is equal to, let's take the linear function, negative 5x plus 1. Okay, now that's just a line, slope negative 5, y-intercept 1. In fact, I'll make a sketch of it over here, which we'll use in a minute for another example. So it crosses the x-axis here, has a slope of negative 5, which says it goes down 5, 1, 2, 3, 4, 5, and over 1, and you're going to put a dot. And so our function is going to come, I kind of missed the dot, just pretend, kind of come like that. Okay, now you know this is the same thing as y is equal to negative 5x plus 1. So let's say we want to find the inverse function that goes with y is equal to negative 5x plus 1. All right, step 1. You're going to, of course, you're going to get this into y equals form, and then you're going to exchange the x and the y. You're just going to swap them. All right, so this would become x equals negative 5y plus 1. Then you are going to solve the new equation for y. And you're going to get, of course, 5y equals negative x plus 1. And then y is equal to negative x over 5 plus 1/5. Or you can write it all as one fraction. Okay, now, this is the original function. This is f of x. And this should be the inverse function. And we write the inverse function f negative 1 of x. So that should be the inverse. All right, now, here's an interesting thing. Let's make a t-chart of some values for f of x. F of x. And that function is, again, negative 5x plus 1. Let's just put in some values that work for this. So when x is 0, negative 5 times 0, 0 plus 1 is 1. When x is 1, negative 5 times 1 is negative 5 plus 1 is negative 4. And one more. When x is 2, negative 10 plus 1 is negative 9. So these all work for the original function f of x. F inverse x, we said was y is equal to negative x over 5 plus 1/5. Now honestly, smart thing to do is to put in values that would make this nice round numbers, but we're going to try these values that we just put in for, this is your x and this is your y. So what we're going to do is we're going to switch those two. So what happens, here y was 1, what happens when x is 1? We get negative 1/5 plus 1/5, which is 0. What happens when x is, let's say, negative 4? We get positive 4/5, negative 4. 4/5 plus 1/5 is 5/5, which is 1. And when x is negative 9, we get 9/5 plus 1 is 10/5, which is 2. Now, if you notice what just happened, the x's and y's in the original function switched places in the inverse function. So the domain of this function became, watch my pen, the range of this one, and the range of this one became the domain of this one. This is the definition of an inverse function. An inverse function occurs when the domain becomes the range and the range becomes the domain of the new function. Now let's go back to our two steps. If you want to find algebraically an inverse function, you exchange your x and y. You solve the first one for y, exchange the x and y, and then repeat the process and solve the second one for y. Now, I want to go up on my graph. This is where I had graphed the original. This is f of x here that you see in black. And what I'm going to do is I'm going to graph this new function, 1, 0, which is about right there, -4, 1, 2, 3, 4, 1, which is here, and -9, 5, 6, 7, 8, 9, 1, 2, which is about here. And I'm going to connect my dots. Again, I sort of missed, but I get something that looks about like this. Now, if you look at those two functions, and I didn't do a very good job of those, but they should be symmetrical. They should flip across the line y equals x, and they don't do a very good job there because I didn't use a piece of graph paper. But this is another characteristic of inverse functions, that they reflect each other across the line y equals x. So I'll try that again in a minute and see if it gets better. All right, now that's how you find an inverse algebraically. I'm going to do another one with you now. Let's take a function that's not linear. How about f of x is equal to the square root of x plus 1. Now, that's your f of x. Now, this is the same as y is equal to radical x plus 1. Okay, so the first thing we want to do to find our inverse, I'm going to switch colors to find the inverse, and I'm going to use the symbol for inverse, which is f (-1) of x. We're going to swap the x and y, so it's going to become x is equal to radical y plus 1. They're just going to switch places, these two right here. Okay, then we're going to solve this for y, and to do that we've got to get y out from under the radical. So let's take an x, we'll square both sides. Okay, and then y is equal to x squared minus 1. So f inverse x should be x squared minus 1. All right, now here's what I want to show you about the graphs. You recognize, or I hope you recognize, both of these graphs from some work we did the last few days. So I'm going to put both graphs here on this axis. This one is y is equal to x plus 1. That's under the radical, so it's square root. It has a horizontal shift left 1. So let's say it looks like that. The other one is x squared minus 1, which is the parabola, which has been dropped down 1. And I'm going to draw it sort of like this. Now, you only are looking at one wing, but look right here. If I draw that line, y equals x, you see how this part, actually, let me just show you. This part right here reflects across this part right here. Now, if you just ignore this part over here, because actually there is another part to this parabola that goes like this, but we don't draw it because it makes it not be a function. So anyway, that's another example of the reflecting part. Okay, now let's talk about if you were asked to draw a, oh wait, I want to show you one more. I've got some time here, I'm watching my clock. All right, let's take this function. Suppose we did f of x equals x cubed. Okay, you know what x cubed looks like. So this is the same thing as y equals x cubed. Now, to find the inverse, f inverse x, we're going to exchange the x and y here. So it's going to say x equals y cubed, and solve that for y. Take the cube root of both sides, and there you have it. So this cube is the inverse of cube root and vice versa. Now we've been saying that. That makes good sense. But now look at them graphically. Do you remember we said cube is a tall, thin graph, and cube root is a short, little, flat, kind of snaky graph like this. Okay, now if you draw the line y equals x, and remember I'm just sketching, so this is not going to be perfect, they should reflect across each other. This is a characteristic of inverse graphs. Now, if you were to see a graph that you didn't recognize, something like this, let's just draw this graph. Starts there, ends there, has a limited domain and range. And you wanted to sketch the inverse of that graph. Here's what you would do. This is the line y equals x. It is, if you remember in geometry, this would be the line that divides the two quadrants into 45-degree angles. And what you're going to do is you're going to reflect across that. Now, some of you are very artistic, so this will be easy. Some of us are not, so this is what we have to do. Take a point, measure to the line, measure it on the same side, and put a dot. Take a point, measure down, measure the same amount on the other side, put a dot. Take a point, measure, put a dot. In this way, you can kind of systematically work your way through. Each time you come out about the same distance that you did, and it's just we're kind of eyeballing it. And eventually you will get enough points drawn so you can make a sketch, and here is what the inverse would look like. Okay, so that's how you can sketch an inverse when you don't have any numbers to go with. You're just looking at a part. Now I want to make one more point, and then we'll have to do the rest in class. All right, so remember I told you that yesterday we were talking about composite functions, and we said if f composite g of x happens to equal g composite f of x, and both of these happen to equal, I got the wrong pen, let me get one that writes, both of these happen to equal x, you've got yourself an inverse. Let me show you what I mean. Like if we let f of x be x cubed, and we let g of x be cube root. These are functions we know that are inverses, so I'm just going to introduce with this. All right, so if I wanted f of g, or composite g of x, remember what that means. It says put the g function into the f function. So that means blank cubed. And the g function would go in there, so you'd have cube root of x cubed. And if you cube the cube root, you're going to get x. All right, now let's do g composite f of x, which says put the f function into the g. Okay, so the g function is cube root of blank. And into that blank, we're going to put x cubed. And the cube root of x cubed is x. So this is what I mean by if f composite g is equal to g composite f, and they're both of those equal to x. You see how the value is x for both of these? Then you have inverse functions. It's another test. You can test graphically, you can test with ordered pairs, and you can test by this rather interesting method of composition of functions. So now your job would be to just make up a function, any function, then find its inverse, and then I'm going to suggest maybe looking at a graph of the two, or finding some ordered pairs that work for one, and seeing if those same ordered pairs work in reverse order in the other. That's all we have for inverses, and hopefully the homework will help reinforce that. And that's all for today. Thanks for listening.